Hey everyone, welcome back, and let's write some more Leetcode today. So today let's solve the problem, lowest common ancestor of deepest leaves. Pretty interesting tree problem for a medium. We generally know that with tree problems, the first thing you should probably think of is DFS or BFS or both. Many times you can solve tree problems with both DFS and BFS. So going through the problem description, we're given the root of a tree. It's a binary tree, so each node is going to have up to 2 children, but not more than that. But it's not a binary search tree, so keep that in mind. There's no sorted property to this tree. So what we want to do is return the lowest common ancestor of the deepest leaves. They give us some terminology here, which is pretty useful. So first of all, what is a leaf? It's a node that does not have any children. So in this tree, the leaves are at the last level. So if you are thinking of like a BFS solution, it's pretty easy to get the last level in the tree. In terms of like the level, you could think of this as the 0th level. Like this node has a depth of 0. This level is 1, 2, 3. When they say we want the lowest common ancestor of the leaves, in this example, it's actually kind of simple because the ancestor is basically like any node that had the path from a node all the way up to the root. So if we want all the ancestors of 7, you kind of just work your way upward. This is an ancestor, that's like the parent. This is the grandparent. This is the great-grandparent. And you just kind of keep going up. Same thing with this node. So when we go up, we see that this node actually already has the same parent as the other one, not even grandparent, but just the parent. So that's the lowest common ancestor. This is also technically a common ancestor, but as you can see, this one is at level 1. This one was at level 2. So we would return this node. And it might be a little bit confusing to you how they showed the output here. They had 2, 7, 4. That's just to indicate that we're not returning the value of the node, we're returning the node itself, because then we get an output of the tree, which is 2, and then it has a left child of 7 and 4. So we're not like deleting these nodes or anything like that. So don't like augment the tree in your solution. So now that we understand what the problem is asking for, how do we go about solving it? Well, if you have no idea how to solve a problem, let me give you some advice. Please start thinking not about the solution to the problem, but about just how to approach it. Think about DFS and think about BFS. You have to think about these algorithms. At least that's how I approach it. That's my thought process. So it's actually possible to solve this problem with both ways. I'll briefly just cover how you could solve it with the BFS, and then maybe if you want to code up that solution yourself, I encourage you to do so, but it's definitely more difficult. Like the implementation is more difficult than the DFS solution. So that's the one that I'm going to be covering. I think in terms of complexity, they're pretty much the same, at least in terms of time. Maybe the space is a little bit different. Just to quickly cover the BFS solution. First of all, this example was very simple. Let's consider a slightly more interesting one. Let me add a node over here, and I don't really care what the value of it is, so I'm just going to put an X. Now, what would be the lowest common ancestor of these 3 leaves? Well, we know all of these nodes are on the same level, so BFS with a picture is very easy. I mean, you could probably tell me what the solution to this is. I mean, obviously you know what the solution is. This is the lowest common ancestor because like 6 is not a common ancestor to these guys over here, but it is of this. 2 is an ancestor of these guys, but not of the other one. But this guy is an ancestor of both of these, so thus it's an ancestor of these 3. Now, how do you figure that out? Well, a pseudocode kind of algorithm would be get all the nodes at the lowest level and then just start working your way up from these nodes. So go to the previous level over here. Okay, well, these are clearly different nodes. They're not the same. So, okay, now go up to the previous level again. Now it's just a single node, so we know that must be the common ancestor. So see how easy a BFS solution is. Now, implementing it is going to be kind of tricky with this like naive way, and I think this naive way might not end up being super efficient, but can you kind of see a shortcut here? If I had maybe not just this tree, but now let me give you an even different example. Let me put a node over here. Let me put like a node over here. Now, the solution to this is that this is the common ancestor. Now, for us to determine that, do we really need all of these nodes and then have to work our way upward? Do we really need to do that? A small shortcut is just to take the leftmost node and the rightmost node and then work your way up, because anything in the middle is actually redundant. We don't need these. We just need the rightmost and the leftmost, because once they converge, then we know we have the common ancestor of everything else in the middle as well. So once you figure that out, this actually becomes like a lowest common ancestor problem that I think we've actually solved before. And I think that's a more simple one. It's just getting the lowest common ancestor of 2 nodes, not 10 different nodes that are maybe on the last level. Now, I'm not going to be coding the solution up, but I've pretty much told you the general solution. But there's another way to approach this problem as well, which is the DFS solution. So let's think about that one. I'm not even thinking about how to code this one up, just so you know. I just start to think about DFS. Okay, if I was over here and I wanted to know if this is the solution, this is the lowest common ancestor, how could I determine that? Well, this is what I would do. I don't know about you, but I would ask myself, what is the lowest node on the left side? And specifically, what is the depth of it? And in this case, we see that, depth here is 1, here is 2, and here is 3. This is 0. So we see that the lowest node on the left has a depth of 3. There are a couple of them, but the depth is 3. If I go all the way to the right side and I ask myself, what's the lowest node on that side? It has a depth of 2. So I automatically know that this is not the lowest common ancestor, because there's definitely going to be one that's lower, because we don't need this right side of the tree. There isn't any leaves in that, like the lowest leaves at least. There are a couple leaves over here, but those aren't as low as these ones. Okay, so now I actually came up with a brute force solution. Like now I can solve this problem in n squared time. That's exactly what I would do. I would go through every node and say, okay, is this guy the lowest common ancestor? And right now we determined it's not. Okay, let me just do a DFS. Let me go over here, ask myself the same question. So it's kind of like a double DFS. I'm going to traverse the entire left tree, entire right tree, and see that, okay, this is not the lowest common ancestor because the leaf over here has a depth of 2. This one has 3. Then I'm going to go over here. Technically, this is a lowest common ancestor. So we would need to be able to handle that in some way and be able to distinguish that this one is a bit different from the other one. Because you could imagine we're given an actual tree that just has a single node, and that would technically be the lowest common ancestor. So we would have determined that this is the lowest common ancestor. But the main way we would distinguish is just by knowing that the lowest leaves were not as low as a different nodes. And then we would do the same thing over here, and we'd see that, okay, left side and right side are actually the same. And the depth of those nodes is 3. That's bigger than this one. That one actually didn't even have any nodes. We would do the same thing on the right side as well. And this is kind of what makes this solution a bit confusing. That's why I'm saying don't think about the implementation details initially, just think about the problem itself. So here we would see that, okay, the depth of my left node is 2, depth of my right node is 2. So this is technically a node that has leaves, and this is in some sense kind of like a lowest common ancestor, but these are not the lowest leaves. These were the lowest leaves, so we'd need to account for that. This is a possible solution, but it's going to be n squared, where n is the size of the tree, because for every single node, we're going to end up doing a different DFS. Now, there is a lot of repeated work in that, so instead of doing it top down, why don't we approach the problem from a bottom up perspective? The tricky thing here is that with this DFS, we're actually going to have 2 return values. It's just easier to handle it that way. The 2 return values that we're going to have are actually going to be the node. So from here, I'm asking, what's the depth of the lowest common ancestor on the left side and the right side? And I want to know the node itself. There are many, many ways to solve this problem. So this is where things are kind of getting complicated. Now that we're starting to discuss the implementation details, it's getting complicated, even for me to kind of describe them, because there are many ways to do this. We could think of it in terms of the depth of the nodes, but the implementation of that actually gets a bit more complicated than thinking of it in terms of the opposite, which is the height. So that's how I'm going to think of this. Let's say our DFS is going to return 2 values. One is the lowest common ancestor, and the other is going to be the height, or it's probably better to think of this as the distance from the lowest leaf to kind of the root. I know that this stuff is hard to come up with. The only reason I'm able to do this is I've solved many tree problems where you have to have multiple return values, and that makes it a lot easier for me to have intuition to know that this is probably along the lines of the correct solution. And I promise you, once you solve 10 different tree problems that are similar to this one, you will have that intuition as well. I promise you. I'm not saying it's easy, but anyways, let's continue. So if we have these, what's the solution going to look like? Well, let me just kind of dry run through this right now for you. I think that's probably the best thing. Let's say I start at this node. I'm going to ask myself the question, what is the lowest common ancestor in the left subtree? I'm not even considering this node anymore. I'm not considering this right subtree. I'm forgetting that these even exist. I'm only looking at the subproblem in the left subtree because I'm going bottom up. And then when I get here, as you can imagine, I'm doing the exact same thing. I'm not considering anything over here as I was. I'm not considering anything here or here. I'm only looking at the left subtree. Okay, and then when I get here, same thing, but this is kind of like the base case. Well, almost the base case. The base case is going to be when we get to null. So null is when we're going to return a null node for the lowest common ancestor, and we're going to return a height of 0 because it's an empty tree. The height is 0. So same thing on the right side. Now is when we're going to ask the question, okay, I got two values. I got like null and 0 on the left side. I got null and 0 on the right side. So it clearly looks like the height of these two trees is equal, and thus this is a lowest common ancestor. So I'm going to return this as like the node. Now, what am I going to return as the height? Well, what's the height of this tree? It's 1. So that's what I'm going to return. Okay, now I'm going to backtrack, like recursively at least. We're done with this side, so we're going to go back up over here. And when we're over here, now that we process the left, we're going to go to the right subtree, and then recursively, we're going to get to 2, recursively, we're going to get to 7, and then 4, and then those guys are going to return, and when they return, okay, we got a 7, that's like the node itself, not like the value, and then the height of this tree was 1, and then on the right side, we're going to get the node, which is 4, and the height of that was 1, so good thing again, it looks like the height of these two is exactly equal. Fantastic. So I'm going to say that this is the lowest common ancestor. I'm going to return now to my parent, the node 2, and the height of the left subtree and right subtree was both 1. So I'm going to add 1 to that and say, okay, my height is now 2. This subtree's height is 2. So from the perspective of 5, we just got this. And from the left side, we got the node, which is 6 and a height of 1. This is where things are about to get interesting. So please pay attention. Remember, when I'm at 5, I pretend like these guys don't even exist. So what is the lowest common ancestor in this problem? In this tree, what's the lowest common ancestor? We know it's 2. So what are we going to say? Clearly, these are not equal. The heights of them are not equal, so we can't say that 5 is the lowest common ancestor. We can't say that, unfortunately. So what can we say? Well, what are we going to do? We're going to compare the two heights of the tree. Because like I said, 6 in some sense is the lowest common ancestor. It doesn't have children. So how do we know that 2 is better than 6? Because the height of 2, the height of that tree was 2. The height of 1 was just 1. And that height, by the way, we're taking it from the perspective of the parent. Like this is on the same level as this one. We're only comparing nodes that are on the same level. So, of course, we would prefer the one that's taller. Okay, so with that in mind, what are we going to do? This is where it's going to get a little bit tricky. So what we're going to return now from 5 is, in fact, the node 2. But the height of it, we're not going to leave it as 2. We're actually going to increment it to 3, because when we say height, we're not actually looking at the height of the tree. We're looking at the height from there all the way up to where we currently are. Because when I get to 3 and then I ask myself the same question, well, what's the height of the left subtree? Like, does that have the lowest leaves, or does the right subtree have the lowest leaves? I'm going to need this 3, because when I'm on the right side over here, we're going to get that value 1. We're going to say, okay, 1's the lowest common ancestor on the right side, and it has a height of 2. We need that plus 1 for that reason. And so now from the perspective of 3, I bet you know where I'm going with this. 3 is bigger than 2, so this node is the lowest common ancestor. If they were equal, then we would say that the current node is the lowest common ancestor, 3 itself. So this is the bottom-up solution. Now, if all of this made sense to you, but you feel like, damn, this is crazy, I would never be able to come up with this by myself, I want you to know that not only did I feel that exact same way when I was learning this stuff, but I promise you, almost everybody feels that exact same way. Everybody who got really, really good at Leetcode probably felt that exact same way. So please don't feel too bad about yourself. By the way, the time complexity of this solution should be linear since we only visit each node once, and space complexity I think should just be the height of the tree, which in the worst case might be n if it's not balanced. So let's code this up now, and remember that we're doing this with a DFS approach, and also remember, let me zoom in a little bit. The main difficulty with the DFS and this like implementation in general is the fact that we're returning multiple values. We're returning the lowest common ancestor and sort of the height, but we know that it's not literally the height of that specific node. But yeah, so now starting with the base case, thankfully it's not too difficult. If not the current node, we return the tuple null, and we say it has a height of 0. Otherwise, we do a DFS. So we run it on the left subtree, and we expect to get a couple values out of that. The left node, it could be null, and let's say the left height, and this is going to be similar to what we do on the right side. So I'll just kind of copy and paste and change these around now. Okay, so now we know that there's 3 cases. I'm actually going to start with the other 2 cases, or actually, I guess I'll start with this. Let's say the left height is equal to the right height. What are we going to do? Well, we know that's kind of the easy case. That means the current node is the lowest common ancestor because the left and right depths and heights are the exact same. So we can say return the current node and return 1 plus either the left or right height. So just something like this. Just to quickly mention, you might be wondering, why did I have the height and why am I not actually using the depth? Because it would make more sense to use the depth. Well, if we do it that way, I think we'd have like an extra parameter. And I think that solution might work as well. Maybe after I finish this one, I might try that one. But the way we're using these heights, they're pretty much acting like a depth for us. But anyway, so now if they were equal, that's what we would do. What if, else if the left height is the one that's actually bigger than the right height? That's also pretty straightforward to handle. We'll return a pair. We will return the left node. We know that's the lowest common ancestor, and we'll take its height and increment 1 to it. Now, the last case is where we do the opposite, because then we know that the right height was actually greater than this one. So I will just copy and paste this around, changing the variables. So there you go. And then when we actually call this DFS, we will do something like this. Passing in the root, we'll get a couple values back, the node and the height. We don't really care about that, so I'll just name it underscore. And then the node is the one that we actually want to return. So this is the solution. Let's run it. Once again, very sloppy typo. This is left height, not left right. And also this is the right node. I'm getting kind of sloppy, sorry. But you can see here that the solution works. It is very efficient. Like a small variation to code this up, you could have gotten rid of that. And I just like to code it this way, where I put the other case over here. So that's kind of a minor change. But now I want to try to see if we can actually solve this in a similar way by using the depth and by passing in the depth and by returning the depth like this. So maybe if like this height stuff was confusing for you, this might end up being more simple, but I actually didn't code it up. So let's see. Okay, so changing this around, now we have to think of the base case first of all. So if we have null, we probably shouldn't return 0 for the depth. We should probably just take our current depth and add 1 to it. So I'll do this. And the return value from this, so I'll just do some renaming, but that's kind of tedious. And I think this code itself should actually be pretty similar with the depth, because we were pretty much treating the height like as kind of the depth anyway. We were just doing it bottom up. So now with the second parameter, I think our life actually is easier. So I have that and I have that. So here, now we take, when we return, we don't need to have that +1 anymore. So I think that's kind of what simplifies this code. We don't really need the +1 because we already had the depth in the first place. But we should be passing in the depth for the recursive part here. So we should take our current depth, which I guess initially we can say is 0 for the root. So we have that. And then we can say, okay, my left child's depth is going to be my depth +1. So this solution actually, I think, is a bit more intuitive. So I'm sorry to have shown you the other one first, but I hope you at least did learn something, because I think that other solution does teach you a lot as well, because some problems do require solving problems that way. So, okay, now let's change this to left depth, this to the right depth. And okay, so when we return here, and we determined that the node is the lowest common ancestor. What do we want? Do we want the current depth? No, I think we can take either the left depth or the right depth since they should be the same. So this is the solution. Let's give it a try. Oh, whoops. I should change this to an else. I don't know how that happened anyway. No, it shouldn't be an else. I'm really stupid. I'm being a little sloppy today. It should be the opposite of just this. I don't know how that happened. Okay, now let's give it a run. And actually, yes, you can see that this one works. And I mean, I don't think it's actually more efficient than the other one. I think this is random. But yeah, I guess the solution might be a bit more simple for most people. If you found this video helpful, check out Leetcode.io for a lot more. Thanks for watching, and I'll see you soon.